Physical supply chains eventually force distinct operations to converge at a single point. Different materials, moving on different timelines, all hit the same physical bottleneck. In operations research, this is modeled as the continuous time joint replenishment problem. Two separate items are restocked on their own fixed, repeating schedules. Ordering each item carries an individual cost, but every time a physical order is placed, it also triggers a shared setup cost, like administration, unloading a truck, or a factory changeover. That setup fee is paid once per occasion. It costs the same whether the warehouse receives just one item or both items at the exact same moment. The optimization objective is to minimize total costs by aligning those two independent schedules. If they meet, they share the setup cost. Achieving these savings requires absolute temporal precision. In this model, the physical logistics problem has been reduced to a rigid arithmetic puzzle. Consider a 30-day window. The top schedule orders every 6 days, the bottom every 10. They align exactly on day 30. The first schedule places 5 orders, the second 3. Because of that shared day, there are 7 distinct occasions instead of 8. One setup is saved. But this coordination is fragile. If the 10-day period shifts slightly, exact coincidences vanish. Past time 0, the schedules never align. Because alignment depends on strict arithmetic commensurability, the financial cost is not a smooth function of the period ratio. This plots total cost against the period ratio. Instead of a predictable curve, the data forms a jagged, discontinuous landscape that standard continuous optimization techniques cannot navigate. To bypass this jagged math, researchers rely on a continuous convex relaxation. But a new exact proof shows this standard shortcut is structurally flawed, understating the true cost by up to exactly 11.19%. The new candidate proof achieves finite exact certification despite this discontinuous parameter space. When the period ratio is rational, the coordination pattern is defined by 2 integers, p and q. A single positive number, t, then dictates the scale of the schedule. This union density formula calculates the distinct order occasions per time unit. The -1 highlighted here represents the exact saving from the shared order. Substituting a fixed pair of p and q collapses all setup and holding costs into a simple calculation for the best scale. However, because there are infinite coprime pairs for p and q, an algorithm must determine exactly when to stop searching for a better ratio. The solution relies on a desynchronized benchmark, or MR. This is the smooth cost approach when coordination becomes so rare that the setup cost is charged separately to each item. By enumerating coprime pairs, the proof establishes a resource-aware tail. This rising bounding curve puts a mathematical floor under all omitted, unsearched rational patterns. Because a shared setup cost makes the true optimum strictly cheaper than MR, the rising curve eventually eclipses the incumbent cost. At that intersection, the infinite search stops. The algorithm generates an exact certificate of optimality without having to check the rest of infinity. Most approximation algorithms avoid this search entirely by using a convex relaxation. This relaxation modifies the objective function by stripping out the complex density of the combined order schedules. It replaces it with this simple maximum frequency function. That function assumes the best possible theoretical alignment between the two items. It imagines that every order of the slower item nests flawlessly inside the faster item schedule, incurring 0 additional shared setup costs. But perfect nesting is often impossible due to the rigid arithmetic of real-world periods. In reality, incommensurable periods force the slower schedule's orders into the empty gaps of the faster schedule, triggering independent setup penalties. The relaxed optimum is a fiction. It provides an optimistic lower bound that discards alignment information and promises savings that cannot physically exist. So, exactly how wrong is this optimistic lower bound for 2 items with independent frequency limits? The new candidate proof isolates the absolute worst possible ratio between the true optimum and the relaxed optimum. The maximum error occurs at the intersection, where 3 different coordination patterns tie for the optimum. Solving for the cost at this geometric bottleneck yields a quartic polynomial with a root at approximately 1.111. This means the standard relaxation can understate the optimal 2-item cost by at most roughly 11.19%. Admissible real coefficient instances in logistics can mathematically attain this exact limit. The maximum error happens near a specific normalized cap ratio of approximately 0.7509. At this point, coordination patterns labeled 1-1, 1-2, and 2-3 converge. The relaxed lower bound sits far below this multi-way collision. This three-way tie for the true optimum creates a structural bottleneck where the relaxation's assumptions fail most significantly. To prove this 11.19% gap is the absolute upper bound, the researchers had to cover the entire parameter space. They normalized any 2-cap instance to a baseline, leaving the space defined by 5 non-negative cost coordinates. They blanketed this space using 4 feasible periodic choices: the nested ratio to the right, the nested ratio to the left, their Ferry mediant, and the direct cap policy. By constructing a weighted average of these 4 policies, the proof verifies that at least one is always within the gamma factor. This is a producer-side, solver-independent replay that awaits formal proof assistant verification and peer review. The theorem applies to continuous time, deterministic, stationary 2-item models. It does not cover the integrality gap for 3 or more items, pointwise capacity, stochastic demand, or multi-echelon effects. While multi-item alignment remains an open problem, this exact certification provides a rigorous benchmark. It quantifies what is lost when we simplify the arithmetic of time, defining the precision limits of supply chain modeling.